Hello and welcome to this introduction to Tcl tasks. The goals of the task package are twofold. Tasks were created to simplify the use of Tcl threads. Tasks can be used instead of or in addition to using the Tcl threads and Tpool collection of commands. Tasks present a model that is familiar to Tcl programmers, the procedure, or Tproc for short. Tasks comprise two high-level meta commands that are sitting on top of 5 lower-level commands. Programs can either use the 2 meta commands or the 5 lower-level commands as convenient. Meta is here being used to mean code that writes other code. Tasks create code dynamically that load into the threads that are created. Tasks are 900 lines of pure Tcl code defined inside a single task's namespace and can be simply copied from a wiki page and pasted into a suitable text file. If the file is named appropriately and placed in the right folder, one can simply do a package require tasks to load it as a Tcl module, or it can be packaged up as a full-on standard package if desired. It can also simply be sourced into a program or even just pasted in. The packaging method chosen is up to the user. Tasks are called with a standard Tcl arg list similar to any procedure, command, or method. A task can be called with a script as an input argument, so nothing is lost by focusing on arg lists. But as we will see, this makes it easy to convert existing procs into tasks. The design of the task module is a 3-level hierarchy. At the lowest level, we have 5 commands. The first, task, is used to create a single task or single thread that has a job queue. Like a thread create, it also has a script. In that script, there's typically 2 commands, twait and treturn. Twait waits for a job, which is an arg list, and treturn returns a value. Any task or the main thread can call another task using tcall, and it can wait for a result using tvwait. Tcall can be used synchronously or asynchronously. At a higher level, there's a command called tgroup, and its job is to create end tasks that each share a single queue. This gives you the ability of a single queue multi-server arrangement. Tgroup also sends jobs, which are arg lists again, to the shared queue concurrently, and any available task in the group can remove a job from the queue and process it and return a value. Tgroup also creates an array where the return values are stored. The top of the hierarchy, at the highest level, is the Tproc command, which looks very much like a regular proc command with a name, args, and body, but in addition can have some options following. The options are such things as the number of threads to create, a list of procedures to import, and a set of initializers, such as package require commands. Tproc was designed to be able to take an existing procedure and simply convert it into a multitasking group of threads. So we're going to begin with an example of a use of Tproc, and it will also use tgroup, since this is the easiest way to use the tasks module. So for our example, we're going to use the math library routine Fibonacci, which I've copied out of the library and I've pasted it here, so you can take a look at it and see how we would use it with the Tproc system. But first, here's the way we would include the tasks module in our program. We use the Tcl module path command to add a path. In our case, the D drive in the stuff folder will contain the task module, which we can see here in, with the standard form of the name of the module, a dash, version number, .tm. After we specify the path, then we can just say package require tasks, and it will find it and it will load it. It knows if it's a module that it's just going to source it. After we've got it loaded, we use this namespace import so we don't have to fully qualify the names of the task procedures. Next, we do a little bit of initialization. We open the console, we size it and position it, we get rid of the TK window that we don't need, and we output some information about what version of Tcl we're using and the size of the pointer, so we'll know whether it's a 32-bit or 64-bit, because I have 4 possibilities we can use here. And we'll see that there's interesting speed-ups when we move between 32-bit to 64-bit, and then finally 8.7 is pretty fast. Anyway, here is the Fibonacci routine. The key here is that the parameter n is going to be used in this loop, and we're going to be passing in numbers of the order of 100,000. So this loop, going from 1 to 100,000, and ends up working with some rather large numbers. So this is a pretty intense test of Tcl's big num system. Then we have a second procedure, and that's fib size, and all it does is it calls Fibonacci with a number, and then it calls string length on the result and returns a text string that says here's the number and here's how many digits long it is. Now, in order to use this, we use a for each loop, and we have a set of 8 very large numbers, all over 100,000, and we put our answers in an answer array, and we're going to call fib size, and we're going to be passing in these numbers. And when this is done, we can get our results output quite nicely just by using the print array command. Now, surrounding this code that's doing all the heavy lifting, we have a few statements here which time how long it takes and outputs it. Since it's a large number of microseconds, we use the comma routine that just makes the number look pretty. Now, after it outputs this, it's just going to go into a wait so it doesn't execute the code that's below this, which, as we'll see later, is the Tproc code. So let's run this, and we'll run it with a 64-bit Tcl for starters, version 8.612. As we can see, this took 6.7 seconds to compute these, and that's because these numbers here, the 100,000th Fibonacci number is 20,899 digits long. So you can see why this took 6.7 seconds. Now here's, interestingly, if I move this over, and if I run this using an 8.7 that I have, you'll see that it's actually a good deal faster. 5 seconds versus 6.7 seconds. And if we run a 32-bit version, you'll see it's a good deal slower. And this one is 10.8 seconds. So evidently, big nums work better on 64-bit systems. Okay, let's close these now, and let's take a look at how we would do this code using Tproc. Now, what we've done is we've taken the procedure that we're interested in is fib size, so we turn that into a Tproc, and all we've done is we've really just put a capital T. We're giving it a different name because otherwise it will collide with this definition of fib size. So we'll have a second one here. It calls Fibonacci just like the other one. So the rest of the code, these 2 lines are exactly the same. Now, after the body is where we have our options, and the options here are to create 4 tasks, meaning 4 threads. This is an option that says don't import all of the task procedures, just import the 2 main ones that it needs. And Fibonacci is part of the list of proc imports, and so this code here will end up being imported into each of our 4 tasks, so that each thread will have the Fibonacci code, and the Tproc code is automatically imported into each thread as well. Now here is the equivalent of the for each loop up here, except that all of these are going to be done concurrently. So tgroup is going to find the queue for fib size t, and he's going to place these arg lists. Now this is actually 8 arg lists. Each arg list is, by being only one parameter here, one value, we don't need to use the list command or put this in braces. But each of these could be more than one parameter. If your arg list took 3 parameters, then you might have a list of 3 items, another list of 3 items, and so on. Now, the run option to T group says launch tasks on all of these by placing these in the queue. Now, there's more of these than there are tasks created. Now, we're doing that on purpose for this first try at it. So all of these end up going into the queue. The first 4 will get pulled out very quickly and will be processed, and the remaining 4 will sit there waiting in the queue. And as soon as the first 4 tasks are done, they'll go off and try and get something else from the queue, and they'll find there's 4 more. So each of the tasks will grab another one. And what we'll end up with, well, this command here, will show us how it processed it, which tasks did work, and how many arg lists did they work on. So in order to run this, we're going to need to comment this out so it'll continue on. So we're going to run this. Well, let's do the 64-bit one. First it's going to do the sequential version of this, which again took 6.7 seconds, but it only took 2 seconds to do this with 4 tasks. Now notice that the results here are in this array, which is the same name as the Tproc name. And so that's why the parray command here spit this out, like these lines here. And this one spit out something that just also stored in that array using the index threads is how many threads you were working with, so you can introspect a little bit and get some information back. Now, notice that in the sequential version, we were putting them in an array called answer. Here, fib size t array is maintained by the tgroup command automatically, so that we don't have to set anything up for that. But if you notice, the answers are the same, and you see these results are pretty large, over almost 21,000 digits each. Okay, now for fun, let's run this with 8.7. And first it's going to do the sequential version. And here's our results. Let's make that a little bit bigger so we can read it. And you see the results are the same. Once again here, we see that here's our 4 tasks or threads, and each of them, this is the count, so each of them did 2. And so the sequential version went from 6.7 seconds down to 5, and then we got down to 1.4 seconds versus 2 by doing this with tasks. Now the next thing let's try is let's see what happens. Then let me keep that on top. Let's change tasks to 8 and see if there's any difference here. First we'll run the 64-bit version. So nothing's going to change with the sequential, but okay, this was the 64-bit version where we ran with 4 threads. Here's 8 threads, and we went from 2 seconds down to 1.4 seconds. So by doubling the number of threads, we gained a fair amount. We didn't gain double because these are only hyperthreads. This is an Intel chip that has 4 cores and total of 8 threads. But what we can see here is that when we dump out the counts, each of these 8 tasks each did 1 job, where before, when we only had a total of 4 threads, each of them had to do 2 jobs. And now for a little taste of 8.7. We get a good speed up here. So somebody did a fine job in 8.7, where we have, let's see, here's a 64-bit system with 8 threads, and 5 seconds, 5.1 versus 6.8 sequential, and 1.4 got us down to 0.923 seconds. So nice improvement there. Anyway, so that's a little taste of how one can use the Tproc command with tasks. Thanks for listening.